Hello and welcome to online lecture number 13 for Chemistry 1101 in the spring semester of 2020. In this lesson, we'll start a new chapter, chapter 10, which is all about acids and bases. So first, what are the properties of these substances? Acids and bases have a variety of very important applications, both industrially and especially biologically. Life as we know it would not exist without these substances and their properties. So acids tend to be very corrosive substances. Corrosive means that they tend to react with materials that other substances don't react with. This makes them both very dangerous, but also very practical. There are very few substances that can react with metals, dissolve metals, eat through concrete, but acids are one of those types of substances. This is probably one of my favorite safety warning signs because it basically implies that if this substance, this acid, is able to presumably eat through a block of metal, it's also able to eat through your hand. So when we deal with acids, especially very concentrated acids, then it's important we take the proper safety precautions. The typical chemical property of acids is that most acids react with metals to produce hydrogen gas. So as an example of, I think, zinc added to an acid, and it reacts to produce hydrogen gas, and you can see that by producing billions and billions of little bubbles. Another property, another way we can identify acids, as we'll get into a little bit later, is that they tend to turn a special plant dye called litmus from blue to red. And so we have what's called litmus paper. Litmus paper is a piece of paper, type of paper that's been covered with this litmus substance, and we take a blue litmus paper, you dip it into an unknown solution. If it turns red, then you know nothing else. You know that solution is acidic. And so it had the properties of acids. In foods, acids tend to have a sour taste. So the sour taste that we either desire to test about certain types of foods, such as lemons, vinegar, other citrus fruits, the sour tasting candies, those are sour because of the acids that either are naturally present or with respect to candies have been artificially added. Whereas bases are also known as alkaline substances. A lot of ways, these are the opposites of the acids, as we'll see. They also tend to be corrosive though, but their reaction though is that they tend to react with oils and grease. And so our most common exposure to bases might be with drain cleaners. Drain cleaners you add to a clogged drain, and then the base, the substance in that bottle drain cleaner, reacts with oils and grease and other unmentionables that might be clogging up the drain, react with it and convert it into a soluble substance, essentially a soluble soapy substance that you're then able to clear with additional hot water. And this reaction of oils and grease to produce soaps has been known for centuries. For hundreds of years, people have made soap by reacting a base, lye, with animal fat to produce soaps. And of course, many years ago, in one of the sort of side plots of the movie Fight Club was they also made soap from human fat, though, not animal fat. And bases, though, because of this typical reaction with oils and grease, in my opinion at least, I think bases tend to be maybe more dangerous than acids in a lot of respects. Because with an acid, when an acid gets on you, when you're exposed to an acid, you immediately know it because there's a stinging sensation. You may have felt this already. Outside the chemistry laboratory, if an insect has bitten you, that stinging sensation may be due to an acid that insect has left in your skin. So you understand what that stinging sensation is. Also, if you ever cut onions and your eyes start to water, they start to burn a little bit, that's because the onions release a substance which gets into your eyes, reacts, and produces an acid, and that also produces that stinging sensation as, I think, a defense mechanism for the onions. So with an acid exposure, you immediately know something's wrong, and you're able to get first aid right away. With bases, though, you can get a base on your skin, and you may not know it for several hours later. And in all that time, the base has been doing damage. Because your first indication that the base is on your skin, maybe that your skin feels slippery. It feels like you went to the restroom, you wash your hands, but you weren't able to fully rinse off the soap off your hands. Because literally the reason why that your skin is now feeling slippery is because the base is reacting to oils and grease and fat of your skin, and converting very slowly, but it is converting yourself into your own soap. So this can happen and take several hours perhaps, and in all that time, damage may have already been done. With bases though, they also react with plant dye litmus, but they turn red plant dye litmus into blue. So you could take a piece of red litmus paper, dip it into an unknown solution. If it turns blue, then you know it's a base substance. And whereas acids have a sour taste, lemons and vinegar, bases tend to have a bitter taste. So mustard, most medicines have a bitter taste to them because of the bases that are part of that substance. So these substances, in a lot of ways, have opposite properties. One's acidic tasting, one's bitter tasting. One reacts to oils and grease, one reacts to metals. So they tend to have these two opposite properties, but they do react with one another. And if you combine the right acid and the right amount of acid with the right base and the right amount of base, they can neutralize each other. So you could take literally a substance that could eat through concrete. You could take that substance and the right amount of that substance, combine that with another substance that will convert animal fat into soap over time, or clear your drain, two very caustic, corrosive substances. But if you combine them in the right ratios, in the right amounts, then what you'll be left with after the reaction's over will literally be salt water, which will be perfectly fine. So these acids and bases have those properties, and there's various ways we can define these acids and bases. Probably the definition that's most useful for our purposes, these last couple of lessons, is what's called the Bronsted-Lowry definition, Bronsted-Lowry theory of acids and bases. And the idea is that with Bronsted-Lowry acids, we can identify a Bronsted-Lowry acid because it's a substance that can transfer and does transfer a hydrogen ion, so an H+. So this is a hydrogen atom, which is one proton and one electron, after it's lost an electron, because it's positive one charge. So this is literally just a bare proton. So for example, HCl, we call it hydrochloric acid, is an acid because in this reaction, it is able to donate a hydrogen ion to water, and then the water goes from H2O to H2OH plus, also seen as H3O. So this H3O plus is what's called a hydronium ion. This is a pi-atomic ion that's formed when an acid reacts with water and the water accepts that hydrogen ion. So as the HCl becomes Cl minus, it loses a hydrogen ion. H2O becomes H3O. And I just wrote it this way just to see kind of where that hydrogen came from to form this hydronium ion. Likewise, nitric acid, also an acid because it reacts with water to produce this hydronium ion. It loses a hydrogen ion, and then what's left after it's lost a hydrogen ion will be the nitrate ion. This is the first time we've seen this notation, this double-headed arrow. We're used to seeing the single-headed arrow. Very briefly, this indicates that this reaction is reversible, which means that not only does HCl and water react to produce hydronium and chloride ion, but at least potentially the chloride ion and hydronium could react to kind of reproduce the original reactants. So that's what those double-headed arrows indicate, and that's actually usually a more accurate representation of what's happening with acids and bases. But for our purposes, we can largely ignore these double-headed arrows and just kind of interpret it as a single-headed arrow. Just a one-way reaction, in other words. Whereas a Bronsted-Lowry base, so if a Bronsted-Lowry acid substance can transfer a hydrogen, can lose a hydrogen, then the base, this opposite type substance, must be able to then accept a hydrogen because the hydrogen has to be able to go somewhere. So Bronsted-Lowry base is able to accept a hydrogen. We see that with sodium hydroxide. You see that maybe more clearly with this Bronsted-Lowry base called ammonia. This is the base that's part of Windex and other type of glass cleaners, where the ammonia reacts with water. So it's H2O, but it's written here differently just so we can see where the hydrogen comes from. Hydrogen is then added to the ammonia. So ammonia, NH3, becomes NH4 plus. So it adds a hydrogen, and because it's adding to H plus, it goes from a neutral charge to a positive one charge. The water molecule, because it's losing a hydrogen, goes from H2O to just OH, goes from a neutral molecule because it's losing H plus to a -1 ion, hydroxide ion. So you can see that in these two examples even, that when acid reacts with water, it produces a hydronium ion, and when a base reacts with water, it produces a hydroxide ion. And that's always going to be true for these bronzosylate acids and bases, is that one of the products of an acid reaction with water is hydronium. One of the products of a base reaction with water will be the hydroxide ion. So a lot of respects we can then consider and explain the properties of those acids and bases we mentioned briefly in the previous slide by the fact that the hydronium ion is the acid ion. That's the ion that's present in all acidic substances. And that ion and its concentration is largely responsible for its properties of the acid. Whereas hydroxide ion is the base ion. It's the ion that's present in base substances, and it's the ion and its concentration that's largely responsible for the properties of bases. So hydronium is the acid ion, and hydroxide ions are the base ions. With bases, we see two different types, typically. We see most bases we consider are simply ionic compounds, soluble or moderately soluble ionic compounds with hydroxide as part of the formula. It's like sodium hydroxide, potassium hydroxide. These are soluble ionic compounds. So when you add to water, they'll break apart into their individual ions, the cation and the anion. And because the anion is hydroxide, then that's how we can explain the base properties of these substances. One example of that, besides sodium hydroxide is typically your drain cleaner, solution of sodium hydroxide is your drain cleaner. Milk of magnesia is a mixture of magnesium hydroxide. So it's a basic substance that you may drink if you have upset stomach due to excess acid. You drink the substance, milk of magnesia, and it's able to neutralize, react with some of that excess stomach acid and neutralize it, make us feel better. And then other types of substances are ammonia and ammonia-like compounds are also a very important classification of bases. So ammonia and then sort of other molecules that have very similar structural features compared to the ammonia. So you've seen even the two examples of the previous slide, like nitric acid with water and ammonia with water. Nitric acid is behaving as an acid because it's losing a hydrogen ion to water. Well, then water is acting as a base because it's able to accept the hydrogen ion. And we know that water is a base in this example because it goes from H2O to H3O plus. So the difference before and after picture, so to speak, is that the water molecule has gained a hydrogen ion. And if the molecule has gained a hydrogen ion, by definition, that means that it's a base. Whereas in our second example, the reaction of water with ammonia, ammonia reacts with water produces ammonium and hydroxide. Ammonia is behaving as a base, and because it's gaining a hydrogen ion, but where is it gaining the hydrogen ion from? It's gaining the hydrogen ion from water. So water loses the hydrogen ion, goes from H2O to OH minus. So in this example, water is behaving as an acid. So whereas most substances are either acids or bases, they either are able to donate a hydrogen, transfer a hydrogen as acids do, or accept a hydrogen as bases do. Some molecules, and a very important molecule will be water, can act either as an acid or as a base. So it can have one or two roles, one or two jobs, depending upon what the other substance is. And so we call these substances that are able to act either as an acid or as a base as amphiprotic. And that's going to have very important consequences as we get into classification of solutions as acidic or basic. So if a substance like an acid is able to donate a hydrogen ion, structurally, it must possess at least one so-called acidic hydrogen. It must have one hydrogen that's able to be easily donated. The bond between that hydrogen and the rest of the molecule must be able to be easily broken. And we won't get into details about what distinguishes a acidic hydrogen from a non-acidic hydrogen, but we see that from the formulas, because we want to be able to distinguish the acidic hydrogens, the hydrogens that are able to be lost versus those that aren't. By convention, this is not always followed, but at least for our class it will be. By convention, if the substance is an acid, then the hydrogen will be listed first as part of the formula. So HCl, this is acidic hydrogen, it's listed first. H2SO3, this actually has two hydrogens that it's able to lose. Whereas this is acidic acid, and whereas acidic acid does have four hydrogens, this one and then these three, we write the formula this way to indicate that, yes, it does have four hydrogens, but because of its structure, because of how those hydrogens are bonded to the rest of the molecule, only one hydrogen, this hydrogen, is the acidic hydrogen. It's able to actually donate it to water or other types of bases, other bases, whereas these three hydrogens are not able to be donated. So acids must have at least one acidic hydrogen. And we see with water, water does have one hydrogen, one acidic hydrogen, and so it is able to act as an acid in certain circumstances. Whereas bases, they must possess, their structural feature, they must possess at least one lone pair of electrons because they're able to accept a hydrogen ion. Remember, hydrogen ion is just a bare proton, doesn't have any electrons associated with it. But if a base is going to form a new bond, all bonds involve at least one pair of electrons, 2 electrons. The hydrogen ion doesn't have any electrons to begin with. So the base must be able to supply both electrons to form that bond. And so, in other words, it must have at least one lone pair of electrons that it's able to use to form this new bond with the hydrogen ion. So water, we see it does have at least one lone pair of electrons. Fluoride ion, the ammonia molecule, and hydroxide ions all are bases because they have at least one lone pair of electrons. So structurally, acids must have at least one acidic hydrogen. That's listed first in the formula, and bases must possess one lone pair of electrons, as we see from the structure. So as we said on the previous slide, water is an amphiprotic substance, which means it can behave either as an acid or as a base. So if we have pure water, or even any type of aqueous solution, most of the molecules in that substance, and not all the molecules in the substance, are water molecules. So what may happen is that 2 water molecules can actually react with each other. If that happens, then one substance acts as an acid, it loses a hydrogen ion. One substance acts as a base, it gains a hydrogen ion. So one molecule, the base water molecule becomes hydronium, the acidic water molecule becomes hydroxide. So one molecule loses a hydrogen ion to the other water molecule to produce, notice, an acidic ion and the base ion in equal amounts. And it turns out that for any type of aqueous solution or even pure water, there's an important property due to this reaction. It says that the concentration, and these brackets indicate molar concentrations, molar concentration of hydronium times the molar concentration of hydroxide must equal some constant. And that constant at about room temperature is 1 times 10 to the minus 14. So this is a very, very low number, but it tells us that in an aqueous solution or any pure water solution or pure water, the product of those 2 numbers, the product of the concentration of the acid ion times concentration of the base ion, concentration of hydronium times the molar concentration of hydroxide, that must equal 1 times 10 minus 14. So you can see, even with that, that as one number increases, the other number has to decrease because their product must equal some number. And so we can use that, as we'll see in the next slide, to be able to calculate the concentration of one if we know the concentration of the other. So notice before we get into calculations though, that because the product of these 2 numbers is a very, very small number, that means that in pure water, both these numbers are very, very small, very, very low concentrations of both the acid ion and the hydroxide ion. If it's in pure water though, this is the only relevant reaction. So from the reaction, the Bounce equation, we produce 1 mole of hydronium and 1 mole of hydroxide. So they're both very small and they're equal to one another. And if we do the calculations, we find that they're not only equal to one and they're very small, but specifically equal to about 1 times 10 to the minus 7 moles per liter, which is a very, 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 very low concentration. It kind of gives us an idea of how low the concentration that really is. If we were to convert that concentration, that moles per liter number, into something more conceptual, what that means is that in pure water, because of this concentration, that means that there are only 2 water molecules are ionized. There's only a net 2 water molecules that actually undergo this reaction for every billion water molecules that are unionized. So if we're able to look at the individual water molecules and count 1 billion water molecules, all but 2 of them would just be neutral water molecules. Only 2 of them would be in the form of either hydronium or hydroxide. So that kind of gives you an idea of sort of the needle in the haystack, how rare this reaction actually is. But even though it's rare, even though these numbers are very small, it does not mean that they're not important. And so then we can classify an acidic substance based upon how these 2 concentrations compare to one another. And the hydronium ion is the acid ion, the hydroxide ion is the base ion. If you have more of the acid ion than the base ion, then we call that an acidic solution. If the reverse is true, if we have more of the base ion then the acid ion is a basic solution. And if, for example, in pure water, they're the same, then we call that a neutral solution. So we can, if we know these numbers, we know the hydroxide concentration, hydronium concentration, or if we know one, as we'll see, we can calculate the other, we can then determine whether we expect that particular substance, that particular solution, to behave as an acid would, or as a base would, or as a neutral solution would. So we want to end with just a couple of calculations of calculating the concentration of one, knowing the concentration of the other. So the first question is calculate the hydroxide concentration if we're given the hydronium concentration is 2.5 times 10 to the minus 4 molar. So we always have this relationship, concentration of hydronium times concentration of hydroxide will always equal 1 times 10 to the minus 14, whether it's in pure water or an aqueous solution. That's always true. So if I know one, I know this number, I can always calculate the other. So in this case, we know hydronium is 2.5 times 10 to the minus 4 molar. We want to calculate the hydroxide concentration. So we can rearrange this equation to solve for hydroxide. There's one approach we could take. It says the hydroxide concentration then is equal to 1 times 10 to the minus 14 divided by the given hydronium concentration. We plug in our number, 1 times 10 to the minus 14 divided by 2.5 times 10 to the minus 4. And this is scientific notation, so it's very important that we practice these because it's very easy to make mistakes with scientific notation in our calculator. So the answer should be 1 times 10 to the minus 14 divided by 2.5 times 10 to the minus 4 gives us a molar concentration of hydroxide of 4.0 times 10 to the minus 11 molar hydroxide. So this says that in a solution, aqueous solution, if we know the concentration of hydronium is this, then it must be the concentration of hydroxide is this. And the second question, we're going to calculate the hydronium concentration of a solution given the hydroxide concentration is 1.8 times 10 to the minus 9 molar. So once again, the important relationship is the concentration of hydronium times concentration of hydroxide must equal 1 times 10 to the minus 14. So here we know the hydroxide concentration and we're asked to find the hydronium concentration. So to solve for hydronium, I want to rearrange this equation and do so. It's equal to 1 times 10 to the minus 14 divided by the hydroxide concentration. So we plug in our number. Hydronium concentration is equal to 1 times 10 to the minus 14 divided by 1.8 times 10 to the minus 9 gives us an answer. So I encourage you to practice these on your own as well as before, because it's easy to make mistakes with calculators and scientific notation. We get a hydronium concentration then of about 5.6 times 10 to the minus 6 molar hydronium. So if this is the hydroxide concentration, the hydronium concentration must be 5.6 times 10 to the minus 6 molar. And another conclusion we can draw is that because we know the two numbers, notice that the hydronium concentration, this number, they're both small, but this number is larger than this number. Notice the exponent is less negative than this number. So because, not part of the question, but because the hydronium concentration is greater than the hydroxide concentration in the solution, we have more acid ion than we have base ion, which means this is an acidic solution. And because it's an acidic solution, we can then predict some properties of this solution based upon the fact that we have more acid ion present than base ion present. So we can see that if we know the hydroxide concentration and the hydronium concentration, we can always compare them, and then from that decide whether it's an acidic, basic, neutral solution. As we'll see in the next lesson though, fortunately there's another more convenient way of expressing whether a particular solution is acidic or basic, as well as how acidic or basic the solution is.